Welcome to the video lecture of Comparative Design. This video discusses the topic called Optimization of Module 6. This session pertains to the course outcome, Apply Optimization Technique to Intermediate Code. Syllabus of Code Optimization includes Principles of Optimization and Optimization of Basic Block. We can start with the Introduction to Code Optimization. Intermediate code undergoes various transformation called optimization. So optimization means which all transformations that we are applying over the intermediate code, it is the optimization. Code optimization is done by code optimizer, which is the phase after the intermediate code generator. That means the input to the code optimizer is intermediate code, the output will be optimized code. To make the resulting code running faster and taking less space. That means code optimizer performs optimization so as to make the execution of the code faster and to make the memory consumption low. Optimization never guarantees that the resulting code is the best possible. It is not guaranteeing that the optimization is done to an extreme end. Maybe further optimization may also be possible later. We are considering only machine independent optimization. That means we are not taking into consideration any of the features of the machine while we perform the optimization. The technique used are combination of control flow and data flow analysis. The technique used are control flow analysis and data flow analysis. What is control flow analysis? Where the how does the control flows that we have to analyze, because while we perform transformation it should not alter the control flow. Then data flow analysis means how the data is flowing, whether the data is to be alive till the program get into the next block of statements. Like that things we have to observe while we perform data flow analysis. Usually during the control flow analysis, we can perform loop optimization most often. Which are the criteria for improving the transformations over the code? That means the transformations that we apply over the code, the intermediate code, must preserve the meaning of the program. Second one is it can be applied only if it will increase the speed of execution of the program. Avoid the code optimization that run occasionally or during debugging. Then improvements are usually obtained by improving the source code. So the programmer is always responsible for finding the best possible data structures and algorithm for solving a problem. It is more than the compiler writer. The programmer can produce or provide an optimized code to the intermediate code generator. Then consider as an example, consider the C code for quicksort. Here the C programming language is used for performing quicksort. A function is written over here. Then based on the previous function, we have identified the 3 address code corresponding to each statement of that function. So these are 30 statements correspond to the previous function. Then introduction to basic block and flow graph. We are doing code optimization, that is actually machine independent process or phase. Then it is actually done using control flow analysis and data flow analysis, and it is after performing that analysis we will be applying the transformations. During the control flow analysis, the program will be represented as a flow graph. It is represented as a flow graph. Flow graph means it is a graphical representation. Nodes will be represented representing the basic blocks. Another term is basic block. So this basic block means the sequence of consecutive statement in which flow of control enters at the beginning and leaves at the end without halt or branches. That means if there is some sequence of statement or some set of statement which doesn't have any branching, then that particular set of statements can be grouped as a basic block. So that basic block can be represented as a single node in the graph for the flow graph. And the edges of the nodes in the graph represents the flow of control. So basically flow graph means it is the graphical representation of the 3-address code. That is the set of 3-address code which is not branching can be considered as a single basic block. It is actually the single node. So that means if there are branching statements, we can construct different basic blocks, that means different nodes, and these nodes can be linked using the arrow marks, that is which shows the flow of control. That is the edges of the graph. Then how will we determine the basic block? Algorithm to identify basic block. Then it determine a algorithm to identify basic block means first one is to determine the leader. That is a important thing. We have to determine the leader. That is a new term. The first statement is a leader. Always the first statement will be leader. Any target of go-to statement is a leader. Whole can become a leader. Always the blocks or basic blocks start with a leader. So if a leader comes, that means it is the start of the first basic block. If another leader comes, means it is start of the next basic block. So any target of a go-to statement is a leader. Go to some label. That label can, where the label is encountering, that will be the another leader. Any statement that follows a go-to statement is a leader. Also after the go-to there will be a statement. So that statement can also become leader. That means then another basic block will begin. For each leader, its basic block consists of leader and all statement up to next leader. So that is in the flow graph. In the flow graph, we can see that it adds control flow information to basic block, and in addition to the basic block, which is represented as nodes, there are edges that will represent the control flow. If there is a directed edge from block 1 to block 2, if B2 can follow B1 in some execution sequence, there is a jump from the last statement of B1 to first statement of B2. B2 follows B1 in natural order of execution. Normally if it is following the sequence, then we can draw a straight line, otherwise with an arrow, otherwise we have to use a loop or some arrow pointing towards that particular block which it needs to go. So this previous one, quicksort, its 3-address code and its corresponding basic block is shown. Here how we can identify the label. In this case, we can examine the go-tos first. The initial statement will always be leader. So that means first basic block start with the first statement I is equal to n minus 1. This is the basic block B1 is first statement, it is the leader. Then where this basic block will end, so that means you have to identify the go-to of 5. That 5 is a label. So that means till 4 it will form a basic block. From the 5 onwards another basic block. So till go-to of, if T3 less than V, that is till that it is another basic block. Then again go-to of 9. So till 12, if T5 greater than V, it is a block. Then go-to of 9 means j equal to j minus 1, the same block. So we have shown it as a loop, self loop. Then again we know that the rule says that the statement immediately after the go-to statement is also a leader. So after this go-to again a statement. So that is again a go-to statement. So we can say that if I greater than or equal to j is a state, it's a leader. So it forms the basic block. Also the basic block consists of only that particular statement only, because it includes a go-to. go to of 23. That means that 23 is T3 is T11 is equal to 4 star I, like that. That will be forming another block. Then T6 equal to 4 star I, that is actually some other block. That because here it is going to this block, so after the continuation of go to, it will form another block. So it is shown as B5, and the go to statement, go to 23, that particular set of statement is shown as B6, block 6. And the flow of control is represented based on the go to as a self loop or as a directed arrow. Then coming to the first topic of code optimization, principal source of optimization. There are two different optimization possible. Local optimization means it is optimization performed within a single basic block. Global optimization means optimization will affect different blocks, basic blocks. Then function preserving transformation means it will improve the code but without changing the function involved or included in it. Examples of function preserving transformations are common sub-expressions, copy propagation, dead code elimination, constant folding. These type of transformations, when we apply, it will not affect the exact function of that statements. Also, loop optimization is example of transformation. Inside loop optimization, we can perform code motion, or you can perform loop optimization using induction variable by making use of the transformation over the induction variables, by making use of the strength reduction over the loops. You can examine one by one. This principal source of optimization is also asked as essay. It is an important topic. Common sub-expression elimination. What is common sub-expression? An occurrence of an expression E is common sub-expression if E was previously computed and the values of variables in E have not changed since. It is already computed, that means it comes in common, that is common sub-expression. So that particular expressions, if it is occurring more than one time, we can remove that if it is not affecting the if it is not affecting the any function undersigned by that particular set of statement. So here, when we consider the previous quicksort function as basic block, if we consider this basic block, we know that here T7 is equal to 4 star I, T6 is also 4 star I, T8 equal to 4 star J, T10 equal to 4 star J. We know that 4 star I, 4 star J, they are computed twice. Even after first computation, that 4 star I is not having any change. So when we compute it again, the same result we will be getting. So we can avoid or eliminate that particular redundancies. That is, after eliminating the repeated steps, the block become T6 equal to 4 star I, X equal to A of T6, then T7 equal to 4 star I, that is eliminated. T8 is equal to 4 star J, T9 is equal to A of T8, A of T7 equal to T9. Since we have eliminated T7, is there any T7? So here no T7, only T6 exists, so we have to rename it as T6 equal to T9. T10 equal to 4 star J, again it is not required. A of T10 is equal to X, that will be replaced with the A of T8 equal to X, then go to of B2. That is the example of common sub-expression elimination. Next is copy propagation. Given the copy statement X equal to Y, use Y for X whenever possible after the copy statement. That means if we have a copy statement X equal to Y, try to use Y itself. Wherever it is specifying the value of Y, don't use X, instead use Y. So that if we continue to use Y on the places where possible, we can finally eliminate that assignment statement X equal to Y. That is, example as before, transformation, the block is X equal to T3, A of T2 equal to T5, A of T4 equal to X, go to B2. You know that here T3 is copied to X. But if we, in the third statement, A of T4 equal to X, x is reused. But if we, instead of x, if we are mentioning t3 again here, the block will become like this. After I have written that x equal to t3, a of t2 equal to t5, f t4 equal to t3. Go to b2. Here, when we look into the statement after transformation, we can see that x equal to t3 code is of no use. That means the copies, this transformation together with dead code elimination will give us the opportunity to eliminate the assignment altogether. That means this is the copy propagation. So if we are using this t3 again, we can avoid this x equal to t3 become dead code, and we can avoid this dead code or eliminate this dead code. So copy propagation always usually it gives rise to dead code elimination. Then next is dead code elimination. What is dead code? Which is not live actually. A variable is live at a point in a program if its value can be used subsequently. That is the meaning of live. Otherwise it is dead. So in this case, if debug is true, then print something. Many of the times or always debug is false, then what is the need of checking it again and again? So it is better to give it as debug equal to false. So this is an example of removing an unreachable code, that is the dead code. Another one is constant folding. Constant folding means we have to, if an expression is having some constants itself, we have to evaluate that constant and we can use that value. Suppose if 2 star 3 is x equal to 2 star 3, it is better to give it as x equal to 6. Reducing at compiled time, the value of an expression is a constant, and using the constant instead is called constant folding. That is constant folding. So x equal to 2 star 3, instead of specifying like and as an expression, it is better to evaluate that expression and use it, x equal to 6. There is an example. Coming to the loop optimization, the running time of the program can be improved if we decrease the amount of instruction in an inner loop. This loop optimization can be applied to so many program intermediate statements. 3 techniques useful for performing transformation over loops are chord motion, reduction in strength, induction variable, elimination. Then what is induction variable? A variable x is called an induction variable of a loop L if every time the variable x changes the value, it is incremented or decremented by some constant. That means for I is equal to 0, I less than 10, I plus plus, if such a for loop is considered, I is an induction variable. It is changing often. It is changing by a particular constant. Then chord motion. Chord motion means, so 3 techniques. Out of that, first technique is chord motion. How we can perform transformation over the loop, that is what we are discussing. Chord motion means if we move the chord outside the loop, we can save so many number of expensive steps. That is, look for expression that yield the same result independent of the iteration. Here, if we check an example here, while I less than or equal to limit minus 2, always we have to compute limit minus 2. That means how many times the while loop get executed, that all times the limit minus 2 will be evaluated. So better if we make this limit minus 2 outside the loop, we can avoid that much number of operations or calculations. So t is equal to limit minus 2 is provided as statement prior to while loop, and while I less than or equal to t is given. So that means we can improve the code by moving the code outside the loop. Next is induction variable elimination. Here the j is an induction variable. Consider that block B3 of the quicksort function, j equal to j minus 1, g4 equal to 4 star j. That means now the value of j is 4 into j minus 1, 4j minus 4. So what is 4j? T4 is 4j. So it is better that we can rewrite it as j equal to j minus 1, t4 equal to t4 minus 4. Here we are looking for the strength reduction. Star as a multiplication operator, it is actually having more strength or more number of operations are required then we do an addition operation or subtraction operation. So it is better to replace that expensive multiplication operator by cheaper addition or subtraction operator, whichever applicable. So here we are replacing T4 is equal to T4 minus 4. Instead of 4 star j, it is T4 minus 4. So T4 means it is 4j, that you have to mention before this B3 starts. So T4 minus 4, if T5 is equal to F T4, like that we can continue. So strength reduction means replace an expensive operation with a cheaper operation. So this is the flow graph after performing this transformation. So examine the previous blocks and the blocks you obtained after the transformation. Next topic is optimization of basic block. There are two types of transformation: structure preserving and algebraic transformation. Structure preserving transformation means the basic block's structure or functionality will remain unchanged even after applying the transformation. Algebraic transformation means we can perform algebraic simplifications over the statements. Structure preserving transformations can be common subexpression elimination, dead code elimination, renaming of temporary variables, interchange of two independent adjacent statements. We can discuss in detail. Here common subexpression elimination. Here also how can following code can be improved: a equal to b plus c, b equal to a minus d, c equal to b plus c, d equal to a minus d. Here b is equal to a minus d is used, c equal to b plus c. So this a minus d is again computed in the fourth step. That we can avoid. Instead of that, you can directly give d is equal to b. So that is we have eliminated that common subexpression b plus c computation. Then dead code elimination, if x is not used in the block, it can be removed. So remove that statement. Suppose that x equal to y plus z appears in a block and x is dead symbol, that means it will never subsequently used. Then without changing the value of the basic block, we can safely remove the statement. That means if at all a code is not reachable, it is better to remove that. Renaming temporary variable. Consider the code t is equal to b plus c. Here the temporary name is t. We can change the temporary variable name as u equal to b plus c. That means wherever t is there, you have to replace all t's with the all u's. These all things transformations applied without changing the structure or functionality of the basic block. Another one is interchange of statement. T1 equal to b plus c, T2 equal to x plus y. We can also interchange like this: T2 equal to x plus y, T1 equal to b plus c, if it doesn't affect its structure or functionality. So many of the structure preserving transformation can be implemented by constructing DAG or a basic block, directed acyclic graph, or a basic block. So if you represent a basic block, that means using a DAG, there will be nodes. So the initial values of the variables will be appearing in the basic block. For that there will be node. Then for each statement there will be there is a node n associated with each statement as within the block. For basic block statements, for individual statement there will be node. Then the children of node, that will be the statements, and that statement will depend upon the last definition prior to that given statement s. That means it should be checked that nodes are still alive. Then node n is labeled by the operator applied at s. Then the node is having the list of variables. That means the children node will always depend on the condition of the variable, that is whether it is live or not. Then we can say that some nodes are designated as the output nodes. The output nodes means these are the nodes whose values are live on exit, and it can be used in another basic block of the flow graph. So all things can be clear. more with the help of this example. A equal to b plus c, b equal to a plus d, c equal to b plus c, d equal to a minus d. Now that initially b and c are occurring, so it is their nodes, their values here b0 and c0. Initial occurrence, it is denoted as b0 and c0. The operation, that will be the node. For each statement there will be a node. So corresponding to this statement, the node is plus. A is equal to b plus c. The result is stored in A. So that is why that node, plus node, is named as A. Statement, first statement is named as A, and its children are b0 and c0. Coming to the second statement, b equal to a minus d. B equal to a minus d means a and d are the children node, minus is the operator. So a means it is the output of the previous. So that is the plus node is named as a. So that is the one of the child, and d is another one. So d is the initial value, so it is noted as d0. So next is c equal to b plus c. If before you creating the node, you need to check that whether c already exists and no changes happen to that c. So here the c already exists in the first statement, so that c0 is enough. So you point to that. Then b means the value of the a minus d, that is mentioned in the node corresponding to minus. So that is shown as the left child here. So this plus, so c equal to b plus c means this plus node, its name as c, the child is b and right child is c0. Then the final statement is d equal to a minus d. That means again you have to perform a minus, but before creating the node you have to check for left and right child. Is it still exist without any change? A minus d, a and d are the branches we are expecting, but a it is already existing, that is the b plus c, the result of b plus c, that is a. So that you can use it as a left child. Then d means it is the already existing d0. So that means or this node with the minus itself, that node minus or itself already exists, so this can be commonly named as b and d. B equal to a minus d, d equal to a minus d, that is a common sub expression. So it can be named as b comma d. So after constructing DAG in this way, we can say that there are only 3 nodes. So that means that only 3 statement is required. That means the statements are a is equal to b plus c, then b is equal to a minus d, then c is equal to b plus c. That is required, because again d is equal to a minus d is of no use. But if d is alive, what we have to do? And b is not live. That means we can use like this: a equal to b plus c, then d equal to, instead of b, because b is not live, so we can use d here, b equal to a minus d, c is equal to d plus c. That means here we are maintaining d but not maintaining b, because b is not live. If both of them are live, that means we have to use a b equal to d statement also. Then another term is peephole optimization. Peephole optimization means we will observe a short sequence of target instruction through a peephole and replace that instruction by a shorter or faster sequence whenever possible. That means a small set of statements will be observed through a peeping hole, and within that set statements, if we can apply some transformation, we will apply it. Then again peep. Then further, if any transformation is possible, apply it. Continue it till we can apply more transformation over it. That is peephole optimization. The characteristics of peephole optimization are redundant instruction elimination, flow of control optimization, algebraic simplification, use of machine idioms. Inside the optimization of basic block, it is dealing with the algebraic simplification. That means which all algebraic transformation that we can apply for the basic block. The peephole optimization will allow us to perform so many algebraic transformations. So one of the algebraic transformations is using the algebraic identities. Here x plus 0 is same as 0 plus x, that is same as x. X minus 0 is same as x. So like that, that identity based transformations can be applied so that we can execute the code more faster. Another one is strength reduction. The algebraic optimization includes strength reduction. You know that exponent 2, that is same as x star x. So that means we can reduce it with more cheaper operation. Then another class of algebraic optimization is constant folding. We have already discussed about the constant folding. That thing applies here also. Then another one is based on commutativity and associativity. That means if star is a node, it is commutative. Before building that node in the DAG, so it's suppose we have to perform m star, and m is the left child and r is the right child. If a star node already exists with an n as the left child and m as the right child, it is also okay for this particular operation because both are same, because star operator is commutative. So we can avoid that creation of another star node. Then in the case of relational operators also it helps, because x minus y is already there. We can also name it as x greater than y. We need not produce another node for x greater than y, because x greater than y itself checks x minus y. Then when we use associative laws, that is a equal to b plus c equal to c plus d plus b, the intermediate chord will be here. A b plus c will be evaluated first, then after that c plus d, that will be stored in t, then a equal to t plus b. If the t is not live, that is not required for the block after this particular set of statement, then we can use the concept of associativity and the commutativity. If it's not a problem, we can use the statements like this: a equal to b plus c, then e equal to a plus t. That means already b plus c is having this, b plus c is can be multiplied even it is after d, because there is nothing wrong happens if we do like that, because associativity and commutative rules makes sure that the result will not affect the change of order will not affect the result of the computation. So that is all about the optimization of basic block. So in this video we have discussed majorly two topics: principal source of optimization and optimization of basic block. Principal source of optimization is a very important topic. So many transformations that we can apply over that. So it dealt with the function preserving transformation as well as the looping transformations. Then in the optimization of basic block, we have come to the structure preserving transformation as well as the algebraic transformations. So that's all about the code optimization phase. So after the code optimization, the optimized code will be fed to code generator. Thank you.